Hey everybody, Dr. Retzik here. This is our first video on section 7c, which is all about what are called positive operators. Let's get started. Okay, so let's just jump right in. Here's the definition of a positive operator. Definition: T, a linear operator on V. V here, some sort of finite dimensional inner product space. No specification as to whether it's over the reals or the complex field, is called positive. So that's the term we're defining. If T is self-adjoint, so T equals T star, and inner product of TV with V is bigger than or equal to 0 for all vectors in this space. Okay, so that's what it means to be positive. Now, your book points out, and we should too, if you knew that the scalar field was the complex field, then the hypothesis that T is self-adjoint would be superfluous. You wouldn't need that because self-adjoint would follow because TV inner product V would be a real number for every V. And so by what, like 715, theorem 715, I guess, back there at the start of self-adjoint operators, we would know in that case that T was self-adjoint. So lots of times you see out in the world people say consider a positive operator, and it's only this that they mean. Because they're just assuming that the scalar field is the complex field, and so T equals T star comes for free. But technically speaking, if the scalar field happen to be the reals, then you have to include T equals T star as part of the definition. In any case, this is what we mean by a positive operator. It's a self-adjoint operator such that TV inner product V comes out non-negative. Okay. Now, if you want to build the analogy that within the big box of all linear operators on V, the self-adjoint operators play the role in that box that the real numbers play in the box of complex numbers, then you might start thinking about square roots. After all, every positive real number, non-negative real number for that matter, has a square root. Might the same be true for positive operators? Now, we should be clear on what we mean by square root, so that's the next definition. Definition: R, a linear operator on V, is a square root. That's the term we're defining of T if, when you do R twice in a row, you get T. Okay, so it looks like really algebraic. R squared equals T. That's what it means for R to be a square root of T. 4 squared equals 16. So 4 is a square root of 16. Okay, so the question then becomes, all right, so you have these positive operators. Do they have nice properties? And in particular, should we be expecting that there are square roots of these things? And it turns out that the answer is yes. So the purpose of the rest of today's video is just to write down a bunch of facts about positive operators. So let's label this section facts. Whoa. Facts about positive operators. Okay, So we're just going to write down everything we can about positive operators. Okay, so in this discussion, let T, linear operator on V, be positive. So that's our only hypothesis. It meets the definition above of positivity. Okay, well, let's write down some things. Thing one, T equals T star. Well, no kidding, that's part of the definition. And not only is T self-adjoint, but all eigenvalues are non-negative. Okay, so let's get a grip here. Any self-adjoint operator, the eigenvalues are real. Here we're saying more than that. If you're a self-adjoint positive operator, then not only are your eigenvalues real, they're all non-negative. And it's just so easy to see. So by definition of positivity, that's true for every vector v. Now, if v happens to be an eigenvector that goes with some eigenvalue, then tv would be lambda v. Pull that lambda out in front, and you see that lambda times norm v squared is bigger than or equal to 0, which means lambda itself is bigger than or equal to 0. Okay, great. So positive operators, these are excellent because their eigenvalues are all bigger than or equal to 0. Fantastic. Okay, that was a nice fact. Let's see. Let's go with another one. Since by definition a positive operator is self-adjoint, then the spectral theorem comes into play. Since T equals T star, spectral theorem yields ON basis E1 through En such that, well, T self-adjoint, so whether the underlying scalar field is the reals or the complexes, one of those two spectral theorems apply. And so we definitely have an orthonormal basis of eigenvectors. In other words, with respect to that orthonormal basis, the matrix for T is diagonal. Okay, but hang on. The fact we just proved, fact 1, says that all those lambdas are bigger than or equal to 0. So all those entries down the diagonal are bigger than or equal to 0. So R, given with respect to E1 through En by M of R equals, okay, hang on, all those diagonal entries right here, every one of these guys, bigger than or equal to 0, which means we can square root them. They're numbers, real numbers. So let's define an operator like this. So call that R. That's how R's matrix looks with respect to this basis. Well, if you do that matrix twice in a row, you get the matrix for T. So R defined in that way is a square root. And not only that, this R is positive. It is itself a positive operator. It's clearly self-adjoint. I mean, there it is. It equals its own conjugate transpose in matrix form. But also, the other part of the definition of positivity is met. you should check that. But it really is. That R, where you just square root all the stuff down the diagonal, that is a square root of t. Perfect. Okay, cool. So what did we just show? We showed positive operators have a positive square root. That's good. Nice. Let's keep rolling here. Let's see. What else can we say? Oh, well, in particular, t has a self-adjoint square root, namely the r we just made in the previous fact. Again, look at the matrix for r. It's diagonal, and the entries on the diagonal are non-negative real numbers, so the conjugate transpose is itself with respect to that orthonormal basis. So that r is self-adjoint. Okay, fine. So that's more like just an observation about the thing we made in the previous fact. Okay, cool. Let's see. There exists R, a linear operator on V, such that T equals R star R. Okay, well, I mean, we're kind of beating a dead horse here. The R we just made is that R that we're claiming exists. Yeah, so that just means it's possible to write the positive operator T in the form R star R. Okay, cool. Now, we mentioned that fourth fact because check this out. Fifth fact. From fact 4, you see that T star is R star R star, which is R star star. But R star star is R, so that's R star R, but R star R is T. Okay, cool. So any operator that can be written in this way is self-adjoint. We just argued that. Oops. And not only that, check this out. TV inner product V. Okay, well, T can be written as R star R. And then by definition of adjoint, that's RV, RV. And that's bigger than or equal to 0, just in any inner product space. Inner product of a thing with itself is bigger than or equal to 0. So from 4, here's what we're saying, and this is the real kicker. 4 implies T is positive because we just showed. 4 implies that T is self-adjoint and TV inner product V is bigger than or equal to 0 for all V. Okay, wait, what did we just show? Hang on, back up. This section of the discussion is called Facts About Positive Operators, and it began with this supposition. Let T be a positive operator. And then a bunch of things followed. Fact 1 followed, and then from fact 1, fact 2 followed, and then from fact 3, or fact 2, fact 3 followed, and then from fact 3, fact 4 followed. So T positive implies 1, implies 2, implies 3, implies 4. But then we just argued that 4 implies T is positive. This is a closed logical loop. Every one of these things implies the other. So not only are these facts about positive operators, These are facts equivalent to t being positive. So this is a theorem. T is positive if and only if all of these things. So when you're trying to show that an operator is positive, you are free to show any of 1 through 4, because 1 through 4 imply t is positive, and t positive imply 1 through 4. So they're equivalent. So let's make sure we're clear on that. Grand conclusion, therefore, t, a linear operator on a finite dimensional inner product space V, is positive if and only if 1, if and only if 2, if and only if 3, if and only if 4. And that's the first big theorem here in section 7c. So positivity is equivalent to all sorts of different things. Positive operators are going to play a nice role in our further development of sort of understanding the structure of operators on inner product spaces. Okay, read along in the book, come to class with questions, and I'll see you next time. Bye.